classes. So basically, I'm sharing this for Google Meet, so I'm literally going to record the classes right through Google Meets. It doesn't record you. It doesn't even have any video. It's just going to hear me talking and record everything that's on the screen. So this way, if for some reason you miss class or you miss something in class and you want to go back and look at it, you can. All the videos are uploaded to YouTube unlisted, so anything that you can use YouTube on, you can actually view the video on. So if you try to scroll down a little bit, you can actually see there's like the final exam review for Calc 1 from last semester or last spring. So you can even go back and look at some of the older classes videos. Maybe I explained it a little bit differently or whatever else in those classes. You can actually go back and look at those as well. So the nice thing is why I use this over Blackboard is if you're taking Calc 2 and you want to go back and review some stuff from Calc 1, you still have access to it all. And if for some reason, if you're not taking me for Calc 2, because I don't always teach Calc 2, you can click on Calc 2, and here's all my lessons from my Calc 2 class. So if you really liked how I explain certain things, you can actually just go watch the videos from my lectures and see a different way of explaining it from whatever teacher you have there as well. So, and all my notes and stuff will be up there as well for those classes too. So you have access to all that, which is one of the reasons I kind of do it. So there was a couple of good things that came out of the pandemic, and one thing is having the technology to record classes. So that's there as well. All right. Let's see. So the book you should get should look like this. That should be the cover of the book you're getting. It's edition 9E, and it'll come with the WebAssign. When you log into WebAssign, you're going to see 4 assignments. Those are the 4 homework assignments. That's exactly what I'm going to base my test on. So you actually have a test on chapter 2, 3, 4, and then the final exam, which will be a cumulative one. But these are basically where I'm going to pull the types of questions that are going to be on your test. So if you do the homework and do fine on the homework, you should do fine on the actual test, which we'll talk about more in a little bit. The code you need is right there. It's also on my website on that page there, so you can just copy and paste it into WebAssign. That will be the code that you're going to need for it. Grading, simple. 20% is your homework. So those 4 homework assignments that you saw on WebAssign, that counts for 20% of your grade. There's 3 tests. Each one's 15%. One's on chapter 2, one's on chapter 3, one's on chapter 4. There won't be a test in chapter 5, but that will be included on the final exam. Final exam is 25%. It is a cumulative final exam. And class participation is 10%. So basically, as long as you just don't show up to just show up for the tests, you're going to get the 10%. That's my little fudge factor grade in there. So, any questions on the grading? Okay. On the tests, you are allowed a note card, 4x6, 3x5 index card. You can use both sides. It has to be handwritten. So while you're going through the homework assignments, if you have to look things up, you can write things down on your index card, and you can bring that to the test to use on your test. I don't typically do extra credit assignments on things or makeups for the tests, but what I do is I will take your final exam and I will replace your lowest test grade with your final exam score. So say you did really poorly on the first test and you got like a 50 on it, but you got an 80 on the final. I'll replace that 50 with the 80. So I figured if you can do that well on the final exam, then obviously you understood the material and you're fine for that test. The other side of that is as long as you're getting 90 or above on all 3 tests, you're exempt from the final exam. Okay, so it is not an 89. It is not an average of a 90. It has to be a 90 or above on all 3 tests. Okay. All right. So the basic breakdown, the only day that's odd that we don't have class on February 20th. Okay, it's a Thursday. I had something else that I already had scheduled about 6 months ago on that day. So all the rest of the days will be normal. I don't think there's actually any Tuesdays or Thursdays off except for spring break. So works out kind of nice. All right. Any questions with any of that? Yes.
If I'm not going to meet you for one of the exams, am I able to make it up on there?
Yeah, we'll talk. Which one is it? The first one or is it later one?
The third one.
Okay, that's fine. We'll talk and figure it out then. So, all right. Any other questions? Good. And actually, I think everybody is actually here today, which is a good thing. All right. How many of you did not take pre-calculus last semester? Okay, so only a few of you. That's fine. I will tell you that I believe pre-calculus is harder than Calc 1. Okay. However, I will also say along with that, the number one mistake everybody makes in Calc 1 is not calculus errors. They're algebra errors. They're errors that you should have learned and mastered in pre-calculus and before. Okay. So as long as you did okay in pre-calculus, calculus will be easy. Because I'm just basically going to add one more thing on top of what you did in the pre-calculus stuff. But like I said, most of the mistakes that are made are those algebra mistakes. Remembering how to factor, remembering your trig rules and trig laws, those type of things. Those are going to come up a lot in calculus. So that's why they really harped on those in the pre-calc class. First thing we're going to talk about is limits. Does anyone know what a limit is? And it's not just the thing on this highway. All right, well, let's start off with something simple. How do you find slope?
Y2 minus Y1.
Yep. So we need how many points to find slope? 2. So how would I find slope at that exact point? Could you? How would you try to do it? Huh? Okay. So yeah, pick a couple points on either side of it, right? So let's say if we did 0, 0, and 2, 2. Those are not extremely close values, but they're 2 values. So if I found the slope between those 2 points, I'd get a slope of what? Huh? Nope, I need the equation. I just want the slope. So if we did y2 minus y1 over x2 minus x1, what would be my slope? So it would be 2 over 2, which is 1, right? Okay. So those 2 points aren't exactly close. So let's get a little closer. Let's do 1.5 and actually it's on the other side. 1.5 and 2.25, and then 0.5 and 0.25. So now this one would be m equals 2, right? Okay. So we're getting closer, right? Now I'm going to need my calculator because I'm not going to be able to do this in my head. Actually, I can't that one. Actually, I can. What about these 2 points? That I can't do in my head. It also comes out to be 2. Okay. So what would your guess be for the slope at that point? Probably 2. However, if I did that point if I did, so it was just that one point, I'd end up getting a slope of 0 over 0. Does that exist? No. So the first thing we need to look at to figure out what we're going to be doing with this to find this. This is actually the actually main point of calculus 1, is to be able to find slope at any specific point at any time. Okay. So you know how they claim oh, it's rocket science? That's actually exactly the entire purpose of calculus, because they needed to find out the speed of a rocket or any moving object at every single point in time. Okay. They didn't want to look at 2 points and figure out the average speed. They needed to know instantaneous speed of that object, instantaneous acceleration, velocity, position, those type of things. And that's where calculus really comes into play. Okay. So to do that, we need to start getting closer and closer to a single point, and we need to be able to find values of a function where it doesn't actually exist, like this. 0 over 0 doesn't exist. I can't do that. I can't divide by 0, but I can find a value of it. As we saw, as it's getting closer, it's going to a number. Okay, so that's where limits come into play. All right, so here's this long definition of limits, which basically just says exactly what I just said. You are never going to need to know a definition. Okay, I'm not going to ask a question on the test. Tell me the definition of this. It's not useful, but as long as you understand how to use it, that's the more important part. All right, so let's look at this one. Oh, yeah, other thing. Don't go out and buy a $150 calculator right now. You will not need it. If you have a TI graphing calculator, great. You can use it. Awesome. If you don't, that's fine. You can use Desmos. Okay. All right. So if I looked at the graph of this function, probably should have done this before I started the class. If I look at the graph of this equation, I want to find out what the answer is when x equals 0. Okay, because that was what this symbol right here says. When t goes to 0, what's the value of this? If t is 0, what's the value? It's going to be undefined because, again, I'm dividing by 0, right? All right, so let's look at the graph. If I go to exactly 0, there we go. It tells me it's undefined. However, what happens as I'm getting really close to it on that side? So if I start off over here, that number is getting larger and larger, or not really larger, but it's getting closer and closer to something, right? And as I get closer and closer to it, before I actually get to it, there's an actual value there. 1 point or 0.166667 or 6, it just keeps going. And if I look at this side and I go to it, it's also going to about the same spot, right? So if we look at some values here, so if I put in so as I'm getting closer and closer to 0, what's the value going to? 0.1666, right? So what we would say for this function is the limit of this equals, right, there we go, 0.1667. So even though at 0, the actual function doesn't exist, the closer and closer I get to it, it's going to a specific value. So I would say the limit of that is that value. Does that make sense? So if that's the case, it should just keep staying that value, right? Let's add a 0 to this. Still there. Wait. Now the value is changing again. And if I get really close, now the value is 0. So this is one of those problems that the calculators can lead you astray. All right. So you don't want to pick a value so close to the number that you're looking at that weird things start to happen. So if you look at this, as that value right there gets really, really, really small, the calculator can't go out that many decimal places to do the rounding. So this basically becomes 3 minus 3 on top, which is 0. And the bottom isn't exactly 0, so it'd be 0 over a number, so the calculator gives you 0. Okay? So it's one of those situations that this is understanding how to use your calculator properly so you get the right answer. Okay? Because calculators can do weird things sometimes and not always give us exactly what we want. So you don't necessarily want to go extremely close. That's why I typically stopped at like 3 or 4 decimal places. Oh, shoot, I'm not on there. Okay, so here's a wonderful little thing about this. This is the screen that's showing, not my screen. Sometimes I forget to switch. So if it's not switching, tell me. If you don't see what I'm talking about, tell me. There you go. I will try to remember to look at that screen too. Notice how I put a bunch of zeros in there. They both come out to be 0. It gives me a number that's not actually, not now. Not the 1.66666 that I had before. So this is why when I was looking at the table, or when I set up the table, notice how I was getting closer and closer to it. I wasn't just picking one value. I wasn't just picking a number on either side. I was picking a few numbers on either side. So you can start to see the progression towards it. That's the most important thing. So if you're starting to see, okay, it's 1166, 1166, and this goes, wait, 0.1 or 0.0 or whatever else, and something's wrong. Back out a little bit and see what's going on. Okay. The other nice thing about this type of problem is we have a graph. So you can look at the graph. Okay, what's this one look like it's going to? You zoom in a little bit. It's somewhere close to 0.2. So 0.16 makes sense. 0 wouldn't make sense in that case. Yeah. So in these type of problems, if they're looking for, they'll give you the values that they want you to plug in to fill out the table. The nice thing about the homework is you have as many attempts as you want to do it to get it right. And if it's something comes up on it, like it's not giving me the right answer, just take a screenshot and send it to me, or picture with your phone and send it to say, what's it asking for here? And I'll look at it, be able to tell you. Yeah. Yes. So you got 2 ways to use decimals for your test. You can bring a computer, which makes your life a little easier. Or you can literally just go to the website on your phone. The app and the website's identical. You do not need to download the app for your phone. You can just go to the website and use it the exact same way. Okay? So don't make me take that away by catching you doing something you're not supposed to be doing on your phone, because then everybody has to buy a calculator. and they will know who did that because I will call you out in class. So don't do that. All right. So when you're looking for a limit, we're looking for what it's actually going to, like in this case here. So this one, we've got our limit. Does that make sense? How we're using it? So this is how we can actually start looking at a value that doesn't exist or we don't go to a specific point. All right. Your turn. You can use your phones. It's fine. I know every single one of you has a smartphone on you. Graph this. See what's going on. While you're graphing it, I'm going to graph it. You don't need to put the limit or anything else. You're just going to actually put in the function. Let's look at it. You should have gotten something that looked like you could ignore the table right now because I know you did get the table. Oh, that's kind of cool. That's new. Hold on, let me get rid of that. All right, so you should have gotten a graph that looks similar to that. So what's the limit go to? What's the limit we're looking for? So we're looking at the limit. It's going to tell you what you're going to. So in this case, it's going to x goes to 0. So we're looking for the x value at 0. So while the end behavior is going to infinity or negative infinity, the value in the middle here is not. Yes, you can see that's good. Nope. Yeah. Yeah, you could write it like that. Okay. So did anybody actually do it this way problem differently than I did it, or did everybody do it this way? What's the first thing I asked you in the last problem? Before we graphed it, before we found the limit. What's the value at 0, right? And the last one you plugged in 0 and it didn't work. It got divided by 0. What's the value of this at 0? What was it? Okay. So 1/10,000. What's cosine of 0? 1. X to the third is 0. So the answer is 1 over 10,000. Okay? You did a whole lot of work that you didn't have to do. The first thing you should always check when you're doing limits, plug the number in. If it comes out to be an actual number, 9 times out of 10, that's your limit. There are going to be situations where it's not, and we'll talk about those. But pretty much all the time, that's going to be the limit they're looking for. Okay? So in this case, you could have gotten the exact limit by just plugging in 0. Okay? And you could actually have seen that if I put it on the table. It gives it to you. Desmos does it in scientific notation. You do not have to write your answer in scientific notation. My preference for all your answers is as a fraction, because fractions are exact. Okay? I'd rather a fraction over a decimal any day, unless the problem calls for a decimal. So most of these, when you're doing them, you're going to get decimal answers. It's okay. So in this case, my limit, it goes to 1 over 10,000. All right. What happens if a function doesn't go to a point? So what happens if we have a function that looks like this? Hold on. I'm going to get the actual graph and make that bigger for it now. Just see the graph. Where'd my, there it is. So here we have a graph. So what you'd have in a situation like this would be known as a piecewise function. Remember piecewise functions? Okay. Huh? That was actually just writing the letters there. Okay, I'm like, wait. That's okay. All right. So I'm like, wait, what's that? Thank you though. Good catch. All right. So when you're looking at piecewise functions, this is that 1 out of 10 time where the limits might not come up to be exactly what the value of the function is. Okay. So for example, if I wanted to find the limit of g of x as x goes to 5, okay, that would be right here. That'd be right there, right? What is the value if I plugged 5 into this equation, into this function? It's 1, because it's where that point is. What's the limit as it goes to 5? It's 2. because it's that point right there. Because that's where the equation is getting closer and closer to it on either side. Okay? So the limit is not always telling you what the value is at that point, because a lot of times it won't exist. It's telling you what the equation's going to at that point. So that 1 out of 10 situation where it's not going to be always exactly the value that comes out is when you have piecewise functions. Okay? When you have piecewise functions, you can get crazy things happening. So the limit as x goes to 5 of that function is 2, not 1. Huh? Oh, at 2? I'm going to talk about that one now. That's the next one. So the next thing we want to look at is what's listed here. It's one-sided limits. So if we look back at that wonderful little graph here, at 2, it seems to be going to 2 different values, right? On one side, it's going to 1, and the other side, it's going to a different one. So in this case, we have one-sided limits. In this case, we're only going from one direction, okay? So the first, there's 2 symbols. I'm going to see if I can, I'll just write this, make it bigger. So we have the limit as x goes to a with a negative sign. This is from the left. And then we have the limit as x goes to a from the positive side, and this is the right. Okay, so that little plus and minus that you see up there, that's going to tell you the direction you're going in terms of a one-sided limit. So if you see that little symbol, you're only going from one direction into that graph. Okay. What happened to my, hold on, there it is. So if we look at this graph, this one says the limit as x goes to 2, and it has that negative sign. So which direction are we going? Yeah. So this one right here, we're looking at going this from that side right there. So that one's going to what? That's going to go to 3. If we're looking at it from this one, we're looking at it coming from the right because of that little plus sign. What's that value going to? That's going to 1. If there's no symbol there, we're going from both directions. Do they go to the one spot? No. So in this case, the limit does not exist. Okay. So my complete limit at this point doesn't exist because the 2 values from both directions do not go to the same point. Okay. The 5 one we figured out from on the left side, it's going to what? If we're going this direction in 5, what's it going to? Going to 2. If we're going this way into it, what's it going to? Also going to 2. Since they work the exact same or come out to be the exact same value, the full limit going both directions is also 2. Okay, so as long as the limits, the one-sided limits go to the same point, therefore the entire limit actually exists at that point. Questions with that? Let's give you another one of those to try. Let's do this one. All right, find me those four. You can guesstimate where it is. All right, so what's the coming from the left? What's the answer? Yeah, 0.5. Coming from the right, just over 2, right? So let's say 2.1. So does the actual limit exist? No. What's the value if I plugged in 4? 2.1. So in that case, the function actually exists at that point. If I had done 2, the function wouldn't exist at that point either. Okay. So we were looking at that value, right? Good. All right. I want to know the limit as it goes to 0. So it kind of is this crazy thing as it gets closer and closer, right? All right. So we need to let's find a few points on either side, right? So I know 0 doesn't work because it'd be pi divided by 0, which doesn't work. So where do we want to start? Where's 0? Okay. 0. Oh, hold on. I'm on the other side, so let's do the negative. All right, so what's the value at 0? What's the limit as it goes to 0? Very good listening to exactly the question I asked, even though it wasn't what I meant. What's the limit as I go to 0? Huh? 0? Okay. Let's try a different number. So, because this one kind of, yeah.
That's the every point with the equation. That's your 0 point for the every interval of that amount. So you're going up every interval of 10.
Yeah. So when we're looking at it, we're gonna start to see some really crazy things happening, right? It looks like it's bouncing. So let's try some weird numbers. It's no longer going to 0. Is it going to anything at this point? Okay. This function, if we actually continue to zoom in, see if I can. It literally constantly bounces. It'll never go to a single point the closer and closer you get. So when you're looking at like this one here, this is another one of those situations where depending on the values you use, you might get a false sense of understanding of what's going on. Okay. So we always like to use the simple numbers like the 0.1, the 0.01s and stuff like that. But when you have something that looks crazy when you graph it, maybe play around with some of the numbers a little bit. Okay, because if it was really going to zero, it would still go to zero even with these numbers. Because I'm still getting closer to that value in the middle, right? Yeah. Does not exist. In this case, this is one of those limits that it's not that it doesn't exist because it goes to two different values. This one doesn't exist because it actually doesn't ever goes to a single point. So there's a different ways that we have things that do not exist. So in this case, it doesn't exist because it literally keeps bouncing. The graph over there too. So when I put up the notes for you, so you know what I actually will show you. So the recording is getting anything that's on the screen. So when I switch over to Desmos, that's all recorded. When I post the notes, this is what's posted. So anything I'm doing on this screen here. So like I'll copy over the graphs and stuff like that. So you'll be able to have those in your actual notes. And it's just a PDF, so you can actually download it, print it, look at it, copy and paste things out of it, whatever you want to do. All right. Find me this limit. Why? So if I put a zero in there, the value doesn't exist. But does the limit exist? That's the question. Oh yeah, just because there's a really easy thing here. If I ask you why, don't assume you're wrong. I will ask you why, even if you're right. So don't go, oh, change my answer. I literally just want to know what you're thinking and why you came up with that. Okay. You were thinking this. You were thinking that one. Okay. So, but this is a weird one, as all the ones I've been doing today are. What does the limit go to? So let's look. All right. So the value is increasing and continuing to increase, right? So if I went from the left side, what's the value going to? Going to infinity, right? If I'm going from the right side, what's it going to? Going to infinity. And what do we say about the limits? If both sides are going to the exact same value, that's the value of the actual limit, right? So in this case, this limit goes to infinity, which is a valid answer. Yes. Oh, sorry. So that limit goes to infinity. So even if it goes to infinity, it doesn't mean it doesn't exist. That's an actual value that you can use. So they're getting closer and closer to A. It goes to infinity. It can also go to negative infinity. Either one of those would be valid limits. So you probably remember when you were looking in pre-calculus, those are your vertical asymptotes. Okay. Anytime we have a vertical asymptote, one of these will be true. Either the limit goes to infinity or negative infinity, or one of the sides, one of the one side limits goes to infinity or negative infinity. So all of those will create a vertical asymptote. Why would a vertical asymptote be so important when we're looking at? Think back to the very first question I asked. The very first problem I put on the board. We were looking at what? Slopes, right? Vertical asymptote is what in terms of slope? It's an infinite slope, or it doesn't exist, depending on how you want to actually look at it. Okay. So vertical asymptotes are very important when we're starting to talk about those things. It's a value that doesn't exist in the domain, so we can't find information about that point. But we might be able to find a slope at that point as well. Yeah. And there's ways that as we go through calculus 1 and calculus 2, you're going to learn different ways to be able to deal with those type of situations. Nope, you can't just put a question mark on it. It's kind of like in algebra class when you learn the square root of 25 is 5, and then the teacher put up the square root of negative 25, and then they told you this doesn't exist. And then like when you went to algebra 2 class, your teacher goes, it does exist, it's 5i. And you're like, but my last teacher told me it didn't work. It's that situation. Like actually I had an interview today where we were talking about different levels of math and how the teachers at the lower grade levels and even lower classes, they'll teach you something, and because they don't know really where you're going afterwards with it, they'll say something which is true right then and there, but there's exceptions to that rule going forward and how we think things through. 0 over 0 you were told doesn't exist. Well, it doesn't exist, but I still need to be able to figure out things that are going on at that point. And that's where your limits and those type of things come into play. So, all right. Find my vertical asymptotes for tangent of x. Everything we've done so far has been a fraction, right? This one's not. Huh?
Plus N. 0.
Oh, no, I know what you're trying to do. Not quite that. How can I make tangent a fraction? This is where those trig rules come into play.
Sine of the cosine.
It's sine over cosine. So f of x is also sine of x over cosine of x. So we're really looking for values that make that 0. So the first thing is there any situation where sine of x and cosine of x are 0 at the exact same time? No. Okay. Because in that case, we would have a 0 over 0 situation. We have to figure out what's going on at that point. Because it could be a vertical asymptote, it might not be a vertical asymptote. So there's no situation where it's going to be 0 over 0. So the only ones I need to look at is where cosine of x equals 0. So which values does cosine of x equal 0? Anywhere else? And 3 pi over 2. And then we keep continuing on. So depending on what we're doing at the time, that would be valid, or you could write it this way. It's k, yeah, k plus 1. Yeah, that's it. Where k is equal to 0. No, that's not. It's actually 2k plus 1. That's it. Odd numbers. 1, 2, so on and so forth. Where k is integers. And that'll give you all your vertical asymptotes. Good. Look at this one. So patient receives 150 milligram injection every 4 hours. What is the left-handed limit as t goes to 12? 150. Okay. What's the right-handed limit as t goes to 12? 300. Okay. What do those 2 points mean in terms of this problem? Yeah. Okay, so the 150 would be the low end of the dose in the body. And at that point, the 300 would be the high end of the dose of the body. What do you notice is happening for your low end points? They're raising, but are they going up by the same amount every time, or is it getting less and less? So this actually,
Those look like they're the same, but the high ends look like they're kind of less.
they're actually curving. They're both actually curving. So now nobody has to lie, because nobody ever does this. Do you ever take all your drugs the exact same time your doctor prescribes them at the same time every time? Of course not. Nobody ever does that. And it's like once you start feeling better, you stop taking your antibiotics because I'm feeling better. There's reasons where you don't want to do that. Don't worry, I do the exact same thing. So, but is actually this type of situation. They're not prescribing you 150 milligrams. Okay? Because the only time that it's ever going to be 150 milligrams in your body is the very first dose. Every time after that point, it is getting higher and higher. So after a certain number of doses, it levels off. That's what they're prescribing you. So because the actual medicine in your body will decay over time, it actually never completely leaves your body, but it'll decay over time. So they wanted to have it so that you never actually drop below a certain value before you get into your next dose. And then as it curves up, you're going to find the actual high dose of that's where they actually want your body to be. That's where the medicine is most effective. That's why they tell you to take it at the same time every day. That's why they tell you to finish like your book resident. Because if you don't take it at the same time every day, you're going to dip below or be above that level that they actually want you at. Okay. I think it's my Calc 2 class. There's actually an entire problem on this that we actually figure out the exact value of where it actually comes up for a drug. So my girlfriend was going through nursing school, and I actually sent her that problem. I say, here, you guys figure this problem out. They did it a totally different way than my calculus kids did, but they came up with the same answer, which is good. All right. Find me this limit. Computer sitting in front of you.
I've been doing most of them.
Okay. That's fine.
This one,
I'm like, I don't think you're doing this one in your head.
I think my laptop's dead.
All right, here's your graph. Huh? I don't know. I haven't actually got it yet. Hold on.
Or is it not precise?
Actually, a little less than 0.6. Maybe not. Maybe it's actually, hold on. Nope, 0.6 should be fine. It gets closer and closer to 0.6. So I didn't feel like making a table, so I'm just actually using the graph to do it. And it's getting closer and closer to 0.6. So yes, I'd accept 0.6 as this one. All right, so let's do. See how much you paid attention in physics class. Or if you were like me, never took physics class. Can't graph this one. You don't have any numbers. All right, so m naught, that's the mass of an object. So that's your mass right now. M would be the mass of the object at a specific velocity. And then, so the theory of relativity states that it's the mass of the object at rest divided by the square root of 1 minus the velocity squared divided by the speed of light squared. It's a variation of E equals mc squared. So, what happens as your velocity gets closer and closer to the speed of light? Huh? So your mass would be closer to 0? Okay. So it's not getting closer to 0. So it's not the limit going to 0. The limit's actually going so that the V will be basically BC. So if I made VC, what happens to this problem? You have c squared divided by c squared, which is what? Is 1. 1 minus 1 is 0. Square root of 0 is 0, right? So I can't just plug in the speed of light there. But what happens as it's getting closer and closer?
He's getting larger and larger.
Well, yes, your velocity is getting larger and larger because it's getting closer to the actual speed of light. So the question is as v squared is getting bigger, what's happening to that
We don't
fraction?
know the other side.
What do you mean?
We don't know what. How can we, oh, because it's only asking for.
It's only asking for the left because it can't go from the right because you can't go faster than the speed of light. So that's why they only have the negative one. But
I didn't
thought.
read that until now.
That's okay. Good question. Good thought. So as v squared is getting bigger and bigger, what's happening to the v squared over c squared? It's getting closer and closer to 1, right? So, but we didn't get to exactly 1 because if we get to exactly 1, we're going to be at 0 and we can't do that. So that means it's going to be 1 minus some number that's close to 1, but not exactly 1, right? So that's going to be a very small number, correct? Or is that going to be a very big number? Because that's the question. Is this piece in here is bigger or smaller? Small. Why? Huh?
The gap between B and C is becoming less.
Right. So that fraction is getting closer to 1. So therefore, it's getting closer to the first number that I'm subtracting, right? So it's getting smaller and smaller. Okay. So then the square root of that would be even smaller, correct? Okay. So as a so is the mass on the top changing at all? No, that's the mass at rest, right? So that doesn't change. So if I have a fraction where the top number doesn't change at all and the bottom number is getting smaller and smaller, what's happening to the overall fraction?
Bigger.
It's getting larger. You're dividing by a smaller and smaller number. That means you're getting the final answer is going to be larger. So what happens as it gets extremely close to C?
That is a lot.
Or how do we represent a lot in math? Infinity. Okay. So as you get closer and closer to the speed of light, your mass goes to infinity, which is why we can never reach the speed of light. At least based on the theory of relativity. So that's the whole concept behind why the speed of light is a limit, where like you can't get higher than infinity. So if your mass of the object's infinite at that point, then it can't go above that. Which is why we can't go from the other direction. Was it the high school kids the other day? One kid was saying he had to choose between instant teleportation or moving at the speed of light. And they were arguing about which one would be better. And I told them, I'm like, they're the exact same thing. Because if you can instantly teleport between two things, you still can't go faster than the speed of light because that's the speed limit. So instant teleportation is literally just moving at the speed of light, but since it's so fast, nobody else can tell. So therefore, it looks like you were instantly in that spot. So they're essence,
Reaction time.
the exact same time. Same thing.
Well, I mean, if you could actually move this nearly the speed of light, that's
Well, yes, but that was the thing. It's like if they're basically the exact same concept. Like instant teleportation and speed of light, same concept, same exact thing. Because you can't move faster than it. All right, we're done for the day. See the little red dot up in the corner? At any other point in class, if you do not see that red dot up in the corner, please tell me because that means I'm not recording and you don't get the video.